we saw that when we took an ester under a lithium aluminum hydride reduction that we had an aldehyde as an intermediate, but we couldn't stop there, and the ester was reduced all the way to an alcohol. We're going to take a look at something known as the Dibol protocol, and what this will allow us to do is stop the reduction at the aldehyde. And Dibol is a more mild reducing agent than LAH, and it kind of has a special reactivity that's even different than sodium borohydride. So Dibol stands for diisobutyl aluminum hydride. And structurally it's different than LAH and sodium borohydride in that the aluminum isn't negatively charged. In fact, what we have is a hydride bonded to the aluminum and two isobutyl groups on the aluminum. So that's what Dibol looks like. And in most cases, I'll just write Dibol over the arrow. You could also abbreviate this as just the isobutyl groups, like this. So here's the reaction conditions. We use the Dibol reagent. Very important is the fact that this is done at a low temperature, and we work this reaction up just by adding water. So let me draw the product of this for you. Fairly straightforward. We just end up with the aldehyde. But again, I'm going to write this out. It must be done at low temperature. So let's look mechanistically at how this reaction works and how we can stop at the aldehyde stage. So I'm going to simplify my ester just a bit with an R group. And the Dibol at low temperatures, when you add it to this, the Dibol will come near the ester, and I'm just going to draw it kind of like this. It's a little bit reminiscent of the hydroboration. So the hydride will come and add to the carbonyl carbon. At the same time, these electrons will come up and bond to the aluminum. So we're adding the H and Al across the pi bond. So now we're going to draw a tetrahedral intermediate. Alright, so we get to this, and this is different than the O- tetrahedral intermediate that we get in the other reductions. This is stabilized by the aluminum, and this particular tetrahedral intermediate is stable at low temperature. And that's actually the whole key to this. So what happens next, once all of your ester has been reduced to this tetrahedral intermediate, next, water is added and warm the reaction up. Just warm to room temperature. So as you add the water, a couple of things happen. One, the remaining Dibol reagent gets destroyed. And then the second thing that happens is the water removes the aluminum from the oxygen. So the second thing is you just get this tetrahedral intermediate. So now once you get that intermediate, then it's pretty familiar what happens. You have the O-, that will come down, and you'll lose the OET group. And what are we left with? We're left with the aldehyde. But the key is that the aldehyde can't be further reduced because all of the Dibol has been destroyed. So that's the whole key to the Dibol reduction.